Hello everyone, welcome back into another live. Sorry, I just abruptly cut my previous live and then I started again. I've started feeling sleepy, so now I'm completely fresh. We'll start again. Just to give you a basic overview that what I'll be trying to achieve in this video is we are trying to make our agent as a multi-agent framework. Okay, so whenever we will query something, I'll try to draw something. Draw a skill draw. All right. Let me clear this up. Delete. Um, let's say here we have user, and here we have, let's say, our orchestrator layer. Our orchestrator layer will decide where he wants to redirect our query to. So there will be multiple agents. At least that's what we know, right? And agents will have tools attached. So let's say this is what our setup is. Okay. And based on the user query, our orchestrator layer will redirect that query to specific agent. Now we are clear up to this point. Now, what if user queried, which is something really complicated? Okay, it cannot be solved by a single agent. Okay, I'll try to make some real example. Let's say user is searching for best vegetarian hotels, right? So we might have agent to agent one, which is connected with the tools, and this is specialized in finding hotels. Okay, finding hotels. Then we might have an agent which is specialized in categorizing hotel based on foods. Categorize based on food. So job of these two agents is different. Okay, if we try to understand how it might work, is like, let's say this agent one is just query on internet or maybe Google to find best hotels in the user's location, right? But here, this agent's job is to find best hotels which is has best quality. So this agent might refer your ratings, reviews, okay, all that stuff. So let's say user query, okay, I want list of best vegetarian hotels, right? I want list of all vegetarian hotels. This is your user, this is our user's query, right? Fine. So this is our user's query, and we'll send it to our endpoint. That endpoint will have like a lot of other stuff, but let's not get into that. But it will reach to our orchestrator. Okay, so this is our orchestrator. Let me write it down. This is our orchestrator. Now, so to fulfill this user's query, our agent, this is like combination of multiple tasks, right? First, there's no direct way to find best vegetarian hotel in any area, right? You need to find, there are a lot of other factors also affects this particular query. Let's say hotels might have good um, aroma, but they might not have good food. Okay, you need to check ratings, you need to check is it closed or not, is it still operating. Then there are QSRs, there are proper restaurants, different types of menus, buffet, a la carte. So those type of stuff can be served in the hotels. So it depends on a lot of other factors. So if we divide this task, okay, if we divide this task, the query that user provided, we can divide it in this way. Well, there could be many different approaches, but just to give you example of multi-agent framework, we are taking this example. So first is to list best hotels in users nearby area. Okay, does this make sense? So first, our agent should be able to um, locate all those hotels, list out all those hotels which are best in that particular area. Then, okay, then from the just a minute. All right, I'm sorry, someone was on my door. Okay, so yeah, so we will divide that task into multiple tasks. Okay, so first we will list out all the best hotels nearby my area. Then from that list, based on the reviews, we will filter out. Not we, agent should filter out best vegetarian hotels. Okay, so now this is our simple query. Okay, and simple query with simple approach. But this query could be very complicated, right? User can ask anything. The point is, not always we will be able to answer user based on the in single attempt. Okay, so let's say user asked something, till now we were just querying something simple, and it was able to answer through the single agent, but not always will be able to answer that. So what we need is, we need multi-agent framework. So how this query will work, when we will send this query, it will go to orchestrator. First, obviously, it will list down all, it will divide that query into subtasks. So first task will be our list best hotels nearby users. So that task will be given to the agent which is capable of doing that, which is this agent one. It is capable of finding the hotels which is nearby user. Then we have second task is to, from that list, agent should filter out best vegetarian hotels. So whatever the output we will receive, it should be gone to this agent 2 as an input, and this agent is capable of filtering out all those hotels based on the ratings, reviews, people recommendations, um, so everything that can prove that this hotel is like good vegetarian hotel. So this will be going to agent 2, and then once we finalize our answer, once we receive that, it will be um, served as a output to the user. This is a simple example. I might have chosen wrong example here also, but the whole point is your query will be tossed between multiple agents before it is answered to the user. Till now we were just focusing on single agent. We were querying something, an agent will be answering, and that we were showing to the user. But now on, it will not be the case, because we will be adopting multi-agent framework, which might toss this query in between multiple agents until they found satisfactory answer. Okay, so that's the thing we are trying to achieve. Now let's try to understand this. I'm not completely clear with this concept. So first of all, let's just start with like basic example. Okay, let me start fresh. What is multi-agent framework in Gen AI? Yeah, which that allows multiple specialized agents to collaborate, hand off tasks, and complete the archive, complete to achieve specific goal. Instead of relying on all knowing LLM, it acts like a human team. Okay, expert handles specific part. That's what we just understood, right? Our agents are capable of doing specific things, and we are tossing those queries between each other, and that's how it is working. Agent is given a specific role, targeted prompts, and unique tools. Okay, research agent within a web. Okay, perfect, perfect. So we all know that agents are attached with the tools, and whatever the agent we will pass query to, it will have a specialized tool, unique set of tools. Task decomposition: complex tasks are broken down into smaller one. That's what we just discussed. Manageable subtasks that agents can execute either in parallel or in sequentially. Okay, this is really important. So I don't know how it will decide whether the um, task can be done parallelly or sequentially. What I'm talking about is this: we divide our major query or main query into subtasks, right? But now, as per this information, it can be, after decomposition, it can be uh, completed, it can be run parallelly or sequentially. So I know that is possible. If those two tasks are not dependent on each other, it can run parallelly also, but not sure how um, our s- our architecture will decide when to run it parallelly and when not to run it, right? Okay, so that is something we'll have to figure it out. So I'll keep this as a note, a task decomposition. um, Not here, but I have some notes somewhere at least. Not here, agent notes. Yeah, okay, here, smaller, manageable, that I know. Agents can find how. Okay, this is our question. Find how agent will decide. Okay, perfect. And this is our open questions. Perfect, perfect. Let me okay, perfect. Now let's go back. Then how they coordinates. Okay, hierarchical, supervised, manager agent breaks down the problems, assign tasks, co-worker agents, and compiles the final output. Chat group agents are put into a shared conversation where they converse, review each other's work, and interactively solves the problem. Perfect. Graph based, stateful. Agents are connected via flowchart or a graph where the path of a communication branches or loops back depending on the results. Okay, it's it's kind of making sense. Um, I mean theoretically, but still unsure like how we will do it. Like how we will implement it on an agent level, like for example, how agents will communicate. Okay, this is the one of the query I have. Then how agent is working as a flowchart. Probably this is a lang graph type of um, use case, and then graph where the path communication branches or loops back to depending on the results. So it's not a it's not a path that we will decide. Again, one of the query I have, let's say we have four different agents. Okay, we can't define that agent 1 will always call agent 2. There will be a possibility that agent 1 will directly call agent 4. Depends on the user's query, we'll have to decide the path, and who will decide it, how will decide it, that is still a question. But yeah, it's a good information that we have. It's a graph based stateful. So let's see. Popular frameworks, LangGraph is one that we will use it. Crew AI is from Microsoft. We try to use it. Oh, no, no. AutoGen is from Microsoft. Crew AI, I think it's a build framework built around the rules. I don't know who owns it. Assemble crew of autonomous agent. Okay, fine. It's fine. Both. I mean, all of this works on a same theory that agents can communicate with each other before answering back to user. Would you like me to help you choose the best framework? For now, I do not have. We are not at here, right? We are not at the stage where we will select our framework. Probably we'll go with the LangGraph blindly. I don't have any proper explanation for that. But before that, I want to clarify few questions. Okay. Uh, Find how agent will decide it. Okay. I'll just directly post it here. Which through the three method: deterministic code, hard coded, dynamic LLM orchestrators, okay, or event driven state graphs. Oh, these through three. Okay, okay. I think this is pretty convincible. What it is depends on, I think, the architecture. Primary method deterministic code, hard coded, predefined hard coded logic, human roles. In many production systems, the decision is not left up to the agent. Human developer maps the dependencies beforehand because it is cheaper, faster, avoids LLM planning efforts. Okay, yeah. Then this is again another thing, right? We will have. Okay, let me just. We will have power in our hand, but that might not be the cost effective. Okay, how can I make it? Okay, this is normal. This is, let's say, heading to. Okay, fine. How it is decided? The framework checks the configuration file. Wait, what are we talking about? How it decides? The framework checks the configuration file like via mail or Python script. Example: a Crew AI, if developer sets async execution true on 3 research tasks, the framework automatically triggers them in parallel. Okay, asynchronous. If the working task requires an output of those research tasks, then framework force it to wait until the execution sequence. Okay, I think it's totally depends on the framework, right? Framework is smart enough. It's like a LLM only which decides where to toss that query to. Dynamic LLM orchestration, the manager agent. When the framework uses central um, manager or supervisor agent, okay, the decision is handed over to high tier LLM. Like, okay, perfect. Sonnet. How it decides? The manager agent receives that main prompt and breaks it down into using internal loop, like a React chain of thoughts. A chain of thoughts. Perfect. This is something I was talking about. I wasn't aware that there is a predefined hard-coded logic also. But let's say the decision tree dependency check. LLM evaluates if the subtask B needs data from the subtask A. Okay, routing. If the subtask A find stock price and subtask is to find a CEO name are independent, the manager routes them to a separate. Okay, perfect. Stateful graphs. The framework like LangGraph uses the directional graph where the agents are nodes and the path are edges. Path are edges. Okay. How it decided? Agents are nodes. Okay. This is something we need to, and paths are edges. Okay. How it decided? The system uses conditional routing functions called router nodes. Conditional router nodes. Okay. The decision process, the agent finishes a task and they pass it to output to a router node. Okay, the router powered by mini LLMs or Python, if else logic, inspect the state if the output contains multiple items, okay, that needs independent checking. Example, review 5 separate code files. Okay, the router uses a map reduce pattern to spin up 5 parallel reviewer agents in once. Okay. This is heavy. Now heavy. It's heavy. First thing is there is a hard coded logic. Okay. Um, Let me write it down something. How it will segregate tasks. So there are 3 methods. This should also be our heading. Heading. Oh, sorry. This should also be my heading. Uh, I don't know what just happened. Alright. First is like how it will segregate the tasks. First is like uh, hard coded logic. Hard coded predefined or hard coded logic. Okay, so here the framework checks the configuration file via Python script. This is perfect. And then for example, if we create okay, perfect. This is really important information I have. Execution pre okay. And then the dynamic orchestration is the manager agent. The manager agent and the flowchart approach. Okay, difference between LLM manager agent is, let's say, the query received, there will be a manager agent which either be your chat 4.0 GPT, or let's say cloud 3.5 sonnet, which is like powerful LLMs. And how it decides is it breaks down your task into internal loops like a react or chain of thoughts. And dependency check. Okay, if LLM evaluates if subtask B needs data from subtask A. Okay, this is something taken care by LLMs only. Routing, if subtask A finds a stock price, both are independent. Breaking, if the subtask C requires the data from the both A and B, then the manager pauses and waits for the execution of subtask C. Okay, perfect. So it divides the task and it waits. So this is really important. There's another approach they have. Um, it it divides task. LLM divides task. Okay, LLM height. This framework uses supervisor agent, and it divides query into subtasks, and then LLM only decide, right? It's a or you can say the manager only decides. Who decides it? Decision process. LLM evaluates. Okay, LLM only evaluates. LLM evaluates if LLM evaluates if any task is dependent on any other task. Accordingly, it either executes in parallel or in sequentially. Perfect. Now, stateful graph routing. So it's like a React. It's like a internal loop. Uh, okay, this is important line. Perfect. Now there is another type which is stateful graph routing. I am like more into this right now. Uh, I obviously want to try out this React pattern, but then there is another good choice is LangChain. This all is like really good information. I'll just keep it copied. Perfect. So here, okay, here we will keep all our agents in a node, and the connection between them will call it as a ages, right? And if agent one finishes its task, let's say, yeah, so node one finishes its task, it gets handed over to router node, and router node decides, well, now router node could be your hard coded logic, or it could be your LLM also, which decides whether where the next this query or this output will be gone. And then I think they reduced map reduce pattern. Okay, router reduce the map reduce pattern to spin up the 5 parallel reviews agent at once. Okay, perfect. Okay, I think there is a nice video also. Perfect. I think this is worth watching video, but I don't have like 29, 30 minutes. I'll watch it later on. Um, for now, we have to make decision. It could be wrong, but we have to make decision. Um, what should I do? Should I go with the nodes? Well, I think slightly. I think like this graph routing and this lang graph is advanced concept compared to React pattern. And obviously, this human in rules, I don't think we have to waste our time understanding this, because no one really might be using it. But even if someone is using it, it's not hard to understand this, right? Because once we understood how LLMs routes it, it's it's easy to keep a configuration file and force your system to use that configurations. So it's not that hard. So I will go to, well, my intuition is to use this. This is first step. Should be our first step. uh, yeah, let's go with this. Okay, let's take a challenge. Let's go with this. My only concern was, I was aware of this lang graph, and this is like very powerful. uh, But before we use LangGraph, how should we use it? I'm not sure. I think let's use LangGraph. Okay. 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 Uh, let's use LangGraph. Okay. First of all, we have to understand. Here's how the LangGraph um, decides between parallel systems and sequential system under the hood. The LangGraph decision is entirely based on the graph topology. The sufficiently only you connect your agent nodes using edges. It does not guess. It it follows the mathematical structure of the graph. Okay, define agent nodes, researcher agent. Okay, writes the agent, both researcher agent and finish. Okay, researcher agent. Okay, add our agent as a node. Okay, node. Okay, fine. Ages. Now, which one is connected to which one? Agent 1 is connected to agent 2. Start parallel execution. LangGraph sees the multiple edges leaving start to different nodes, automatically boots them up concurrently using the Python async IO, parallel execution, sequential execution. Start. Start is parallel, and then the age is like sequential execution with a join. And graph, okay. Add ages. Researcher 1 waits for it output and then go for the writer. But how the what is this writer? Huh, yeah, for incoming ages. Automatically pauses writer until the both. Okay, this is the name given to our node. Okay, perfect. So writer should wait until researcher 1 and researcher 2 should output. Parallel fan out. When you invoke a graph looks like a start node. It sees two outgoing paths running in research 1 and research 2 because those nodes have zero dependencies on each other. Graph puts them into, uh, well, I think I should be drawing something here. Okay. Let's say we have this, what do we call it? I think this is our, okay, let's say this is our researcher 1, this is our researcher 2. This is our orchestrator, and this is our researcher. This is your write something, right? This is writer agent, a write agent. Now we have this as a nodes. We have these three as a nodes. So let me remove this first. Let's not make it complicated. So we have this three as a nodes like this. Now, um, add a node. This is something adding a node. Fine. This thing adding ages. So add age. This can, okay. Uh, yeah. So this is connected with this, right? And this is also connected with this. See, add age between researcher 1 and the writer, researcher 2 and the writer. Okay. We have the ages. So ultimately, answer will go to researcher agent. So, and whenever we will start, let's say this is our starting point. How to write it? This is our starting point. Or let's not complicate this. Let me bring this. This is start. let's say whenever we will start, the start can be uh, the start can be either go this can either go to researcher 1 or researcher 2, right? Researcher 1 or researcher 2. But a writer agent will always have to wait until either researcher 1 completes or researcher 2 completes. That's why we are adding ages and we are keeping it hold. Okay, this line is keeping writer hold until researcher 1 completes, and this one will complete it. But then this is something not LLM based, right? It is something that we are uh, forcing agent to wait. This is like a this is like a hard coded graph, we can say. It's not a smart one, I personally feel like. But let's see how it works. So what it is saying is, if you invoke the graph invokes the start node. It invokes the start node. It sees two outgoing paths. It sees two outgoing paths running to researcher 1 and researcher 2, because those nodes have zero dependencies on each other. So this obviously this can go parallelly as per this. Okay, what is the example here? This runs simultaneously okay, this is not a great example. It should have given like the proper real life use case, but unfortunately we don't have it. Anyways, fine. We have this researcher 1 node, we have 0.01 second. Okay, and e- okay, let's say uh, it sees two dependencies, which is these two dependencies. Even if researcher 1 finish within 0.01 second, LangGraph will freeze the execution path to writer. It creates a barrier and waits until the researcher 2 finishes it and writes its data into a agent state. Okay, so this is how it this condition works, right? It doesn't execute, it doesn't end here until these two completes it. Perfect. Even if researcher 1 finishes, okay, fine. Sequential execution. Once the parallel, okay, wait on, hold on. Synchronous barrier. This is synchronous. This will go to this will go to this. Sequential, how then? Okay, I understood this. Now let me try to use some different color if I can. I don't know if that's possible. Anyways, so uh, how can I separate? Okay, fine. So what what they're saying here is, if we have sequential path, which is this one, this is our sequential execution. LangGraph detects that the writer has a multiple incoming edges. Writer has multiple incoming edges. It automatically pauses writer until the both parallel task finishes. Okay, so here, even if we execute sequentially, this and this should get completed, then only writer will end. Okay, and in this case, it's not like that. It either first or second will come and that will finishes it. Let's see how the parallel execution works. Once all the parallel inputs are gathered in a state, the barrier lifts. Okay, and the LangGraph triggers the writer, or potentially the writer now safely reads the combined data from the both researcher without any data conflicts. Would you like to see how make dynamic using the conditional router? Okay, yeah, this is what our concern is. This is our concern was like, this shouldn't be like a frozen uh, graph, right? Um, for me, till now it looks like we've decided a path. Okay, we've decided like this will execute parallelly. Okay, fine. This will execute sequentially. Okay, fine. But this is not a case always. User can ask anything, and there should be a way to respond to user's query based on the query that user user asked, right? And looks like this conditional router can be the thing. Okay, let's see. Yeah, tell me how conditional router works. Well, looks like this is like huge concept because we are just scratching the surface. There are different ways. I need to watch this video also. Then I need to follow this. Where is it? I need to follow this different steps. Okay. Hardcoded logic, let's forget. But this dynamic LLM orchestration as well as graph routing, which is just seeing right now, we'll have to explore a lot. But anyways, let's just try to understand this a little bit more, and then we'll start our coding. In the lang graph, the conditional routers allows the graph to make dynamic decisions at the runtime based on the current data in the state. Yeah, that is really important. Now, instead of drawing and fix it from the node, um, node AB points the node A to routing function. The function, which can be Python if else or statement or LLM calls, reads the state and determines the next node activate. Here's how it works. Okay, let's try to understand this. Planner agent fine, worker agent fine, final aggregation fine, dynamic router fine. Okay, now adding a nodes, perfect. Okay, let's try to draw this example also. Where is my okay skill draw here? Okay, perfect. Okay, now we have three different agents. Hold on, planner agent. Okay, where is it? Yeah, this is our planner agent. Then we have what else? We have worker agent. Then we have aggregator agent. Worker agent, aggregator agent. Perfect. Start with a planner. Perfect. Routing logic. Dynamic router is in between. That is a game changer. Worker agent. Test the graph. This route is allowed to point to the worker agent. Okay. So there will be dynamic router in between. So it will be something like this, if I'm not wrong. So this is connected to this, and obviously this will like this is starting with a planner. Then uh, let's say we have start here, start here. Then it will go to planner first, right? It will go to planner, and then let me delete this. I'll just write it down nicely. Then from planner we will be going it to dynamic router. Now what? Now most probably after planner we can give a list of all the available agents here. If it is relevant, we can, I think, pass aggregator agent also here. Tells the worker agents to head to the aggregator when done. Yeah. Okay. So this then why tells the graph router is to allow the point to the worker. The planner agent decides. Dynamic route. Dynamic route could be your function. Ha. Router state. This is a router. It looks like a state. Returns a list of send object to trigger parallel execution. Request state returns worker agent. Sends the copies of the state to the worker agent. For every subtask found, this creates the parallel execution on the fly. Okay, 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 okay. Oh, okay, this is much deeper. So dynamic, okay, planner agent will divide your task into like multiple subtasks. Those will be handed over to worker agent. Those will be handed over to worker agent, and this will work in a loop. How can I show loop? This will work in parallel loop. This is not looking good. This will work in a parallel loop. So dynamic router is taking care of this. Is okay. This is worker agent. Okay. And this is sending, what is this send? I think this is sending the query to LLM. Worker agent results. For every single subtasks that we will receive from the planner. Okay. And then uh, tells the worker agent to herd to aggregator when done. So from worker agent, once the worker agent done with all the tasks, it will go to aggregator. Agent will go to aggregator. Then aggregator ends it. This is your aggregator. This is your end. Perfect. From aggregator to end, like this. Then your workflow complete. Then your app should be answering back. It's a real separate execution, conditional splits, fan out. Yeah, auto wait. Even though the number of parallel workers are decided completely on the fly, LangGraph monitors them. It keeps the aggregator. Okay, the only advantage is on the fly is based on user's query. It will divide the task into subtasks. Then it will hand it over to worker agent, which will do the all the tasks. And at the end, the aggregator will give proper output. Perfect. I think this makes sense. We have learned like so much in this video. I think this was just a theoretical. We didn't get much time to implement it, but in the next video, we'll try to actually implement these patterns. Okay. I think for now, I think